So, let's start with attendance. Rashawn Allen? No Rashawn. DJ Bostic? Derek Cullen? No. Ray Sear? David Escobar? Mello Haywood? Gail Horta? Logan Cross? Vitaly Leon? Gabriel Lopez? Joseph Romero? Alana Ship? Blake Terrell? Avery Thomas? And Adrian Goddess? Adrian? Okay, more. What? Okay, what's your name? Let me just, because that printout is from a couple days ago, so if you register, no, because labs are on Mondays. Let me just quickly check that. Marquee, okay, well, I'm gonna have to make another one of these, but that's okay. Okay. I'll just have to reprint that. There's two more people in this costume. So, I guess I'll get started with some announcements. The first homework assignment, the getting started with WebAssign, astronomy, is due on Wednesday, the 21st. That's next week, Wednesday. The first homework assignment on chapter 1, on the first part of chapter 1, which is what we're covering this week, will be due Monday, the 26th. So the week after next, on Monday, the second chapter 1 homework assignment will be due on Wednesday, the 28th. I decided to push this back a little bit to give you some extra time. The quiz on chapter 1 will be on Monday, the 26th in lecture. Additionally, there is a significant figures worksheet, which I have copies of up here that you can get. We'll cover significant figures in more detail on Wednesday. Hopefully we'll have time to get at least to introduce them. Your name? I wouldn't try it. Okay. But we'll go over significant figures in more detail next week, but I wanted to get the worksheet out so you can grab it. Your name? Can you repeat that? Oh, okay. Yeah. Leon? Okay. And so I have the significant figures worksheet up here. There's actually enough information on it to do it just with what's on the worksheet, because it does actually describe how significant figures work on it. But I just wanted you to be able to get it earlier, because there's going to be that delay because of the holiday on Monday next week. So our next meeting will be in a week, because we have a holiday on Monday next week. No, there just won't be a lab. The labs are going to start a little later. I screwed up a little in my initial scheduling because it's fine. It'll work out. We'll catch up. So that's that. Any questions? So continuing on with where we were last time, we were talking about the metric system. So the metric system is known as the MKS system from the 3 base units for length, mass, and time. They stand for meter, kilogram, second. And all the units are based off of those 3 units. It's a decimal base 10 system. This is a lot more convenient for conversions for each system because all of your conversions are multiplying or dividing by powers of 10. So all you need to do for almost all conversions in the metric system is just move the decimal point. It's administered by the International Bureau of Weights and Measures, the Bureau International des Poids et Mesures in Paris, and it is the International System of Units, which is abbreviated SI because in French it's System International. And it contains 7 base units that everything is based on. And at this point, as of 2019, all of these units are based on fundamental constants of the universe. So it is possible to define the metric system by literally just writing down relationships with the fundamental properties of the universe, which is very nice. So the unit for length is the meter. The unit for mass is the kilogram. The unit for time is the second. The unit for electrical current is the ampere. The reason it's the electrical current, not the electrical charge, is because it turns out it's a lot easier to measure current than charge. The unit for temperature is the Kelvin, which is a measure of temperature with degrees the same size as Celsius degrees. So there's 100 degrees between the freezing point of water and the boiling point of water. But the 0 point is at the coldest possible temperature there is, absolute 0, which is negative 273-ish Celsius. So room temperature is around 300 Kelvin. 293 is my head there. And Kelvin temperature is convenient because it corresponds to the internal energy of the molecules involved and stuff, but starting in absolute 0 is very helpful, it turns out. There's the mole, which is the amount of a substance. It's 1 mole is 6.022 times 10 to the 23rd things. So a mole of carbon is 6.022 times 10 to the 23rd atoms of carbon, for example. That is used to go from, when you're doing chemistry, it allows you to go from number of molecules to masses in grams and vice versa. And it basically lets you count molecules by weight. There's the and lastly, there's the candela, which is a measure of luminous intensity, which has to do with how much energy lights are putting out. And that is the least used of these, I would say. Base 10 is convenient because all your conversions are multiplying by a power of 10, so you're just moving a decimal point. To go from centimeters to meters, for example, you move the decimal point 2 places to the left. And so on. So like a kilometer is 1,000 meters, as opposed to a mile being 5,280 feet. A meter is 100 centimeters, as opposed to a yard being 36 inches. A liter is 1,000 milliliters, as opposed to like a quart being 32 ounces or 2 pints. And here are the prefixes. Some commonly used ones are mega, which is 1,000,000 times the bit. So the metric system uses prefixes. You have a base unit and a prefix, which tells you how many of that base unit you're talking about. So if you have a kilogram, that's 1,000 grams. A megagram would be 1,000,000 grams. A centigram would be 100th of a gram. A milligram is 1,000th of a gram. There are units for tenth, the ones that we'll use, there are units for a tenth and a hundredth, and then a thousandth, a millionth. They start going by 1,000 each time at this point. Similarly, there exist what prefixes for 10 and 100. They don't get used very often. They're not going to use them in this class. They are deca and hecta, I believe. Then there's kilo, mega, giga, growing bigger. So going through prefixes, for the small end, a tenth is deci, so that's 10 to the minus 1. A hundredth is centi. So deci is a lowercase d if you're writing an extra unit. So a deciliter would be lowercase d next to liter. Centi is a hundredth. Centimeter is, you put a lowercase c next to the meter symbol. That's 10 to the minus 2. Milli is 1,000. That's a lowercase m. That's 10 to the minus 3. Micro, the symbol is a lowercase Greek letter mu, which looks like a U with a line on the front. That's a millionth. That is for micro. So a microliter is mu and L. Nano is a billionth, or 10 to the minus 9. So that's a nanogram, for example. You might see that on medicine. The lowercase n and g, or nanometer, lowercase n and m. Then pico is a trillionth, 10 to the minus 12. And so like a picometer is 10 to the minus 12 meters. And then for going to the bigger units, we have kilo, which is 1,000, lowercase k. Mega is a million. It's an uppercase m. So the one that's important to know the difference between is that uppercase m is big, it's mega. Lowercase m is small, it's milli. That's the only one you're going to have to deal with if there's overlap, but there is at least one problem on, there's a problem on the homework for you to know that difference. And then giga. Giga is a billion, capital G. And then you probably encountered the next level up, which is tera. You know, the terabyte hard drive. The next level up is penta. Each of those is 1,000 times the previous. So 1 times 10 to the minus 3rd millimeters, or 1,000th of a millimeter, can be written as 1 millimeter. 1,000th of a meter can be written as 1 millimeter. So a non-standard unit in the metric system is the liter. A liter is the volume of a cube that is 10 centimeters on a side. 10 centimeters by 10 centimeters by 10 centimeters. 1,000 cubic centimeters is 1,000th of a cubic meter. A liter of pure water will have a mass of 1 kilogram. 1 cubic centimeter of water will have a mass of 1 gram. And 1 liter is 1,000 milliliters. So 1 cubic centimeter is equal to 1 milliliter. That is always the case. It's a very useful conversion fact. So 1 centimeter cubed is 1 milliliter. And and 1 milliliter equals 1 cubic centimeter for all liquids. Liters usually used to measure liquids. And for water, 1 cubic centimeter of water has a mass of 1 gram because the density of water is 1 gram per cubic centimeter. But other liquids will not weigh 1 gram for 1 cubic centimeter. Like, you know, alcohol will be less than 1 gram. And you have a cubic centimeter of mercury, that'll be like 13.5 grams. Because different materials have different densities. A liter is a little bit more than a quart. A quart is 0.946 liters, or a liter is 1.06 quarts. On tests and quizzes, I will give you conversion factors between metric and English or US customary units. I don't expect you to memorize those. But I will expect you to know what all the prefixes mean and be able to do the internal conversions for metric units. A kilogram, it's about 2.2 pounds. It's 2.2046 pounds on Earth. It's the amount of water in a 10 centimeter cube. It's 1,000 grams. There's also a metric ton. There are far too many tons out there. There's the imperial, there's the ton that you use in US units, that's 2,000 pounds. There's a metric ton. A metric ton is 1,000 kilograms. It's the mass of a cubic meter of water. So it's actually really helpful for shipping because 1 cubic meter of water weighs 1 metric ton. So if you're doing density calculations, that's very convenient. So there are 1,000 liters in 1 cubic meter of water. 1 metric ton is 1,000 kilograms. That makes it a little bit bigger than the short ton, the normal ton we use, which is 2,000 pounds, because a metric ton ends up being around 2,200 pounds. But there's also a long ton, which is 2,400 pounds. Units are weird. There are too many tons. The long ton isn't really used anymore. Primarily, I think people use the metric ton these days. But yeah, imperial ton is 2,000 pounds. The metric ton is 2,200. It's a little bit bigger. And it turns out it's inconvenient to use just the raw units, the raw 7 base units. It's difficult to make all measurements using only them. Sometimes you need to combine them and make new units, like we did for the liter. The liter is convenient for volume. So we use derived units, and these are combinations of the fundamental units. So we've used derived units for volume. This is length cubed, so you can have meters cubed or centimeters cubed. We can have derived units for area, length squared, square meters, square feet. And things like speed. Speed is length over time. Meters per second, miles per hour, kilometers per hour. Things like that. And we'll eventually get more derived units. So eventually you get to a point where you have derived units that are complicated enough collections of units that we just give them a name. So for example, unit for force, which is a kilogram meter per second squared. You don't want to write kilogram meter per second squared. So it's called a Newton. And I'll introduce them when they come up. Density is a measure of mass per unit volume. So the density of some material is its mass divided by its volume. The traditional symbol for density is a lowercase rho, the Greek letter rho, but you can also just use a capital D. And it is mass over volume. And I made sure that was a capital D, but whatever. It's mass over volume. It's a measure of how compact a substance is. Now, if we were using the standard units, the units of density would be kilograms per square meter. Sorry, kilograms per cubic meter. And that does get used sometimes. Turns out people in the shipping industry use it. I was a little surprised when I saw it. But more commonly, we use grams per cubic centimeter. And that is because the density of water is 1 gram per cubic centimeter. The numbers are just nicer. It makes things like aluminum be 2.7 grams per cubic centimeter, iron be 7.8 grams per cubic centimeter. Most stuff you encounter on a day-to-day basis, on a regular basis, will have densities that's like solid or liquid with densities between about half a gram per cubic centimeter. I don't know. The low end's a little iffy. Up to maybe 20 grams per cubic centimeter. Nice number range that is easy for people to think about. So the average for the Earth is about 5.5 grams per cubic centimeter. The densest thing you're likely to run into is gold at 19.3 grams per cubic centimeter. I guess maybe tungsten. I think tungsten is up there. These are, but it turns out, if we do a quick conversion, we want to figure out what a gram, 1 gram per centimeter cubed is in kilograms per cubic meter. Well, we can convert this. We have grams and we want kilograms. So 1 kilogram is 1,000 grams. To convert units, you can always multiply by two things that are equal, by the ratio of two things that are equal to each other. We're just multiplying by 1. But we're multiplying by 1 in such a way that the grams will cancel out and I'll be left with kilograms. I'll go into those in more detail in a little bit, but I'll just do a demonstration here. And then we want to get rid of centimeters cubed. So we need to get rid of centimeters 3 times. So we have 100. Well, no, let's do, 100 centimeters is 1 meter, but this is cubed. So we need to do this 3 times. So this ends up being 1 gram times 1 kilogram times 1 million centimeters cubed. Name?
David is 4.
Okay. Over 1,000 grams. This is 7 meters cubed. 1,000 grams times meters cubed. Centimeters cancel, grams cancel, so the grams are canceling, the centimeters are canceling. And we're left with kilograms over cubic meters. And this is 1,000 kilograms per cubic meter. So to go from grams per cubic centimeter to kilograms per cubic meter, you multiply by 1,000. So the density of aluminum is 2,700 kilograms per cubic meter, and so on. It just turns out grams per cubic meter is more practical. Cubic centimeter, sorry. Now, to measure liquid density, it is not, you can measure volume and mass and calculate that, but there is also something called a hydrometer, which is a weighted glass bulb, and where it floats in your liquid tells you the density of that liquid. Has to do with how buoyancy works. Because the buoyant force pushing up anything is equal to the mass of the liquid it displaces. So you could actually use this to measure the density of liquid. So the higher the hydrometer floats, the greater the density of the liquid. So pure water has a density of 1 gram per cubic centimeter. Seawater has a density of 0.125 grams per cubic centimeter. Urine is 1.015 to 1.03 grams per cubic centimeter. Alcohol is less dense, for example. So one of the ways that hydrometers are used, the example that the book uses, is that hydrometers are used to test antifreeze in car radiators. And they're actually measuring the density of the liquid because antifreeze is a mixture of water and a denser liquid called ethylene glycol, usually. And so you're checking that it's not too dilute, basically. I think it checks it. But it's a mixture of two liquids and they have different densities. And the denser the liquid, the higher the hydrometer floats. That is, I personally have never used a hydrometer to check antifreeze, but I have used one and own one. The other common use for hydrometers is to figure out how much alcohol is in the alcohol you just made. Because, for example, if you're brewing beer, what you're doing is you're converting sugars, which are denser than water, to alcohol, which is less dense than water. And so the change in density of your beer tells you how much alcohol is in it, because how much sugar you turn into alcohol. You can also use it to figure out if you're making hard alcohol, which is mostly water and alcohol, how much of that is alcohol. But I've not done that because home distilling is not legal. Also, it's a lot more work and a lot riskier than home brewing. And then when a combination of units gets used a lot and is inconvenient to write down, we give it a name. So a kilogram meter per second squared is a Newton. That's the unit of force. A kilogram meter squared per second squared is a joule. That's the unit of energy. A kilogram meter squared per second cubed, or a joule per second, is a watt. That's the unit of power. We've probably used watts because we've seen them on various electronic stuff. Now, conversion factors are how we go from one unit to another. They relate one unit to another unit. You can convert from British to metric, like go from inches to centimeters. Or you can convert units within a system, go from kilograms to grams, for example. Within a system, the conversion factors tend to be nice whole numbers, and the math is reasonably straightforward. It's generally pretty easy in the metric system because the powers of 10, but reasonably straightforward even within the British system. Between systems, the conversion factors are ugly messes. So for example, 1 inch is the same length as 2.54 centimeters. Therefore, 1 inch equals 2.54 centimeters, and 1 inch divided by 2.54 centimeters is 1. So I can multiply by 1 inch divided by 2.54 centimeters and not change anything. So often it turns out for a lot of things, math, multiplying or adding something that doesn't change anything is a really useful tool for solving problems. So here we're multiplying by 1, so nothing changes. You could also add 0. That turns out to be a really helpful tool for solving problems. So when problems involve simple ratios or proportions, we can generally use the approach of unit analysis. You have a given quantity, a ratio that compares them, and a quantity you need to find. This works for unit conversions in general, but it also works for a bunch of stuff in chemistry, which is the class that I stole these slides from. But in chemistry, there's a whole bunch of stuff that is just naturally related by ratios, and it works the same way as a conversion factor. So you have a given value, a ratio, and what you're trying to find. So for units, you have some given value. Your ratio will be set up so that it cancels out the unit you want to get rid of and leaves behind the unit you want to have. And it will be two values that are equal to each other on top of each other. So here the ratio for kilometers and meters is 1 kilometer is 1,000 meters. So 1 kilometer divided by 1,000 meters. So if you were given meters and wanted to find kilometers, you would set this up and you'd put meters in the denominator to cancel the meters you were given. So if you're interconverting metric prefixes, you need to multiply the given quantity by a known ratio or proportion. So for example, if you want to write 6,023 kilometers in meters, which you might want to do because a lot of the equations for physics and such are built around the assumption that you're working in meters. So 6,023 kilometers is meters. You start with a given. Your ratio is going to be either 1 kilometer over 1,000 meters or 1,000 meters over a kilometer. You have two equal values. 1,000 meters equals 1 kilometer, and you can either put one on the top or on the bottom. Now, we want to get rid of kilometers and end up with meters. So we're going to put kilometers on the bottom to cancel the kilometers that we have and leave us with meters on top. So we have 6,023 kilometers times 1,000 meters over 1 kilometer, and that equals meters. And so kilometers will cancel, and you will be left with 6,023,000 meters. All you've done is move the decimal point 3 places. Now, you may have noticed that was a big number, had a lot of zeros in it. So one issue that can show up in scientific studies is that we have very large and very small numbers. And those are awkward to write because they have a lot of zeros and they're sort of hard to process because all the zeros start to blur together. So for an example, the speed of light is 300 million meters per second. It's 3,000,000,000 meters per second. The Earth is about 93 million miles from the sun. A virus is around 0.0000002 to 0.0000004 meters in size. And a hydrogen atom is about 0.00000000001 meter in diameter. So all of those are confusing the way they're written in standard form. So one way to deal with this is we can use what's called scientific notation. Scientific notation, any number is expressed as a product of a small number, specifically a number between 1 and 10, and a power of 10. And this makes the number much shorter and easier to write, and it makes it easy to see generally how big or small it is. And because it's based on powers of 10 and just moving the decimal point, it is easy to convert back and forth to standard decimal notation. Also, often on calculators, you can write enter values in scientific notation. Usually there's like an E button or an EXP button. It depends on the model of calculator you have. And on your homework, if you want to enter an answer in scientific notation, in WebAssign, you can use a lowercase e. So you would write it as a power of 10 times the power of something times the power of 10. So for example, a million is 10 to the 6. 1 over a million is 10 to the minus 6. So positive powers of 10 are big numbers. Negative powers of 10 are little numbers. So for example, 247, we can write this as 2.47 times 10 to the 2. You can see we move 2 decimal places to the left to get the decimal place after the first digit. So the general way you convert from a regular number to scientific notation is you move the decimal place until it is after the first non-zero digit. So the first non-zero digit here is 2. So we're going to get the decimal place there, we need to move the decimal place 2 places to the left. Every place you move the decimal place to the left, you have to add 1 to the power of 10. If there's nothing there, it's at 0. So this is 2.47 times 10 to the 2. And if you were writing this in the homework, in this form, you'd write 2.47 lowercase e 2. And on your calculator, you might have like an EE button. That's what's on TIs. And that'll put a little uppercase E. But usually an E because that stands for exponential. Because this is sometimes called exponential notation. So 2.47 times 10 to the 2, that is 247 in scientific notation. If we go 1, 2, 3, 4, 5 spaces here to get after the 1, the first non-zero digit. That's 1.86 times 10 to the 5. Here we have 4,705,000. We got 1, 2, 3, 4, 5, 6 places to the left. So that's 4.705 times 10 to the 6. So all big numbers, numbers bigger than 10, will have a positive power of 10 exponent. Small numbers, numbers smaller than 1, will have a negative power of 10 exponent. So here, you notice we'll have to move the decimal point to the right. 1, 2 places to the right to get it after the first non-zero digit. So this is 2.5 times 10 to the minus 2. Here, we need to do 1, 2, 3, 4, 5. That's 4.08 times 10 to the minus 5. And here we have 1, 2, 3, 4, 5, 6, 7. So this is 1.0 times 10 to the minus 7. These are all in scientific notation. Scientific notation is when that decimal point in the starting part, which is also sometimes called the mantissa, and I just like that term. You don't actually need to know that, but when it's immediately after the first non-zero digit, that is scientific notation. But so if you're asked to write an answer in scientific notation, it has to have the decimal point immediately after the first non-zero digit. However, let's say you're trying to write 93 million. You could write this in scientific notation as 9.3 times 10 to the 7. That's sort of the preferred form. But 93 times 10 to the 6 would be the same number. And if I don't ask you to put it in scientific notation, this would be a perfectly acceptable answer. Like, I'm not going to have a problem with that. Because I didn't ask you specifically to put it in scientific notation. If I did, you'd have to write this. And actually, technically, this is in another notation, which you might find on your calculator, called engineering notation. Engineering notation limits the powers to multiples of 40. So it's every 1,000, like where you put the commas. But yeah. But yeah, so I'm not super picky unless I specifically say scientific notation. I'm not going to hear about it. But here, let's look back at these examples. This is that distance to the sun, 93 million miles. I could write it as 93 times 10 to the 6 miles, as 9.3 times 10 to the 7 miles, or 0.93 times 10 to the 8 miles. All 4 of those are right. They're the same number, but the preferred value would be 9.3 times 10 to the 7. And if I ask for it in scientific notation, only this one is in scientific notation. And the engineering notation thing is just a factoid. I will never ask for engineering. So the general rule for if you're moving decimal points around, the power of 10 is increased by 1 for every place the decimal point is shifted to the left, and decreased by 1 for every place the decimal point is shifted to the right. And these rules, +1 for every place to the left, -1 for every place to the right, can be used to both convert to scientific notation and convert from scientific notation. Because, you know, let's say you had 93 million, you move it 7 places to the left to get it into scientific notation. And then basically you move it 7 places to the right to get it, the exponent down to 10 to the 0, and then you're in standard decimal notation. If the power of 10 is 10 to the 0, you don't need to write it, because 10 to the 0 is just 1. And multiplied by 10 to the 0 doesn't matter. So here's some examples of converting some real values. So those examples from the beginning. The speed of light is 300 million meters per second. That is about 3 times 10 to the 8 meters per second. The Earth is about 93 billion miles from the sun. That's 9.3 times 10 to the 7 miles from the sun. A virus is 0.00002 to 0.00004 meters in size. That's 2 times 10 to the minus 8 to 4 times 10 to the minus 7 meters in size. You have to move the decimal point 8 places here and 7 places. The hydrogen atom is 0.0000001 meter in diameter. That is about 1 times 10 to the minus 10 meters in diameter. That actually has a unit because it's the size of a hydrogen atom and it's useful for measuring atoms. It's called an angstrom. It's a 1/10 of a nanometer. But yeah. So in scientific notation, we have a mantissa, some number between 1 and 10, and a power of 10. And to convert a number to scientific notation, you move the decimal point to the position after the first non-zero digit. So the number is between 1 and 10. And the appropriate power of 10, you count the number of decimal places you need to move the decimal point. For when you move to the left, you add positive. When you move to the right, it's negative. So if you move 5 decimal places to the left, you'll go up. That's 10 to the 5, so 950,000 is 9.5 times 10 to the 5th. So here are some examples. 0.0257 in scientific notation. We include all the digits that are shown, but none of the leading or trailing zeros accepted numbers with a decimal point after the digits. Basically, never include leading zeros. We do include trailing zeros if there is a decimal point. We'll get into that in more detail when we talk about significant figures. 2.57 times 10 to the minus 2 would be how you'd write this. Because we've got 1, 2 spaces to the right. So 125.6. How would you write that in scientific notation? Anyone? You keep the 6. Yes. 1.256 times 10 to the 2. Here we have 93 million again. That is 9.3 times 10 to the minus 7. Here we have a negative number. Turns out the only thing you need to do special about negative numbers is just leave the minus sign there. So negative 65,800 is just negative 6.58 times 10 to the 4. It's still a positive exponent because this is still, bigger than 10. It's more negative than negative 10. We're interested in how far away it is from 0. And then here we have 0.000000278. This is going to be 2.78 times 10 to the minus 6. Here is the opposite process. So what do you think 2.57 times 10 to the 2 is in decimal notation? It's just 257. The point, you don't need a 0.0 at the end because there isn't actually a 0 at the end there. But that detail is more of a significant figures thing. 1.25 times 10 to the minus 7 is going to be 0.12345 zeros and 125 because we moved the decimal point 7 places to the left. So there are 7 zeros here if you count the 0 in front of the decimal point. 9.3 times 10 to the minus 4. Yes. 0.00093. 6.580000. I think I said enough zeros. Times 10 to the 4. So this is 65,800, but you have to keep those zeros that were still there, because those extra zeros tell you how precise the measurement was. That's why we didn't add an extra zero here, and we kept these. And then 2.78 times 10 to the minus 1. Yep, that is 0.27. So let's go through some conversions in the metric system. So we use decimals to represent length, mass, and volume. Length is things like meters and centimeters. Mass is kilograms and grams. Volume is things cubic meters, cubic centimeters. These are the metric prefixes. I'm not going to go over them again. So 1 times 10 to the minus 3 meters can be written as 1 millimeter. And when you're interconverting metric prefixes, you express these as ratios or proportions. If you wanted to convert between millimeters and meters, you could use any of the 4 following ratios. These two will do the same thing, and these two will do the same. You notice that, these two have meters on top, these two have millimeters on top. We just change a little how you do the multiply. And when you have something in power of 10 notation and you multiply these two things, so if you had 101.05 times, 10 to the third times 2 times 10 to the fourth. The way this works is you multiply the front parts. So this would be 2.10, and then you add the exponent times 10 to the 7. And when you divide the front parts, and then you subtract the exponents. So if you have 1.5 times 10 to the 7 divided by 3.0 times 10 to the 4, 1.5 divided by 3 is 0.5. 10 to the 7 divided by 10 to the 4, we'll take 7 minus 4. This would be 10 to the 3. And then to get this in scientific notation, it's going to be 5. 5.0 times 10 to the 2. So all of these ratios equal 1. Here, if you wanted to convert centimeters to meters, these are the 4 ratios that are possible. You can either have 100 centimeters to 1 meter, or 100th of a meter to 1 centimeter. And all of these equal 1. So if you wanted to write the conversion ratios between meters and picometers, well, 1 picometer is 10 to the minus 12 meters. So 1 meter is 10 to the minus 12 picometers, or 1 picometer is 10 to the minus 12 meters. And I will generally try and use the ones that match these when I write my ratios, but you can use either one. Here, if we're going to go between meters and micrometers, a micrometer is 10 to the minus 6 meters. So you can have 1 meter is 10 to the 6 micrometers, or 1 micrometer is 10 to the minus 6 meters. And my preference would be to use this one just for clarity, but either one works. When you interconvert metric prefixes, you simply need to multiply the given quantity by the known ratio or proportion and keep careful track of the units. So for example, 6,023 kilometers as meters, while 1 kilometer is 1,000 meters, or 1,000 meters is 1 kilometer. So 6,023 kilometers times 1,000 meters divided by 1 kilometer. So kilometers will cancel. We'll give you meters. And that's 6.023 times 10 to the 6 meters, or 6,023,000 meters. Now, if you need to convert from one unit with a prefix to another unit with a prefix, you can always go through meters, or whatever the base unit is. So here we're going from millimeters to micrometers. So what we can do is we can convert from millimeters to meters, and then from meters to micrometers. And we don't have to do that as two separate steps. We can write it all out as one long equation. So we can first find the ratio for millimeters to meters, and then use the ratio for micrometers to meter, from meters to micrometers. So we start with 1.67 times 10 to the minus 7 millimeters. Then we go to meters, so 1 meter divided by 10 to the third millimeters, or you could do 1 times 10 to the minus third meters divided by 1 millimeter. It will give you the same effect. Millimeters cancel. Then we multiply by 1 micrometer is 10 to the minus 6 meters, and we'll get micrometers. So here, we have 10 to the minus 7 divided by 10 to the minus 3 divided by 10 to the minus 6. So we're going to take minus 7, subtract 3, getting to minus 10, and then subtract negative 6, which is the same as adding 6, which is going to bring us back up to 4. And so to negative 4. And that's, so you get 1.6 times 10 to the minus 4 micrometers. And you can see how I did a similar thing here when I was converting a more complicated unit. So here are some examples. We want to convert 2,057 grams as kilograms. Well, first, the ratio is that 1 kilogram is 10 to the third grams. So that ends up being 2.057 kilograms, because we divide by 1,000 or move the decimal place 3 places to the left. Here we have 1.25 times 10 to the minus 7 meters as micrometers. 1 micrometer is 10 to the minus 6 meters. So 1.25 times 10 to the minus 7 meters times 1 micrometer over 10 to the minus 6 meters. We're dividing by 10 to the minus 6. So we're going to subtract negative 6 from negative 7, which gives us negative 1, or 0.125 micrometers. So 1.25 times 10 to the minus 1 micrometers, or just 0.125 micrometers. 9.3 times 10 to the minus 4 grams as nanograms. Well, 1 nanogram is 10 to the minus 9 grams. So we're going to divide by 10 to the minus 9 grams to get nanograms. So we're going to divide by 10 to the minus 9. So subtract negative 9 from minus 4, which is the same as adding 9, which will give us positive 5, or 9.3 times 10 to the 5 nanograms. 6.58 times 10 to the positive 4 meters as kilometers. Well, 1 kilometer is 10 to the third meters. So we will divide by 10 to the third meters. That will move, we'll subtract 3 from our 10 to the 4, and we're left with 6.58 times 10 to the 1 meters, or 65.8 kilometers. And 2.78 times 10 to the minus 1 grams as milligrams. This, we're going to divide 1 milligram as 10 to the minus 3 grams. So we'll divide by 10 to the minus 3, which adds 3 to 10 to the minus 1, leaving us 2.78 times 10 to the 2, or 278 milligrams. Now, when you convert between the systems, your conversion units can be things like 1 inch equals 2.54 centimeters. So if you're going to convert between inches and centimeters, 1 inch equals 2.54 centimeters. So your ratio is going to be 1 inch over 2.54 centimeters, or 2.54 centimeters over 1 inch. So if you wanted to convert 65 inches to centimeters, 65 inches times 2.54 centimeters divided by 1 inch is 165 centimeters. The inches cancel out. If you're going to memorize any metric to English unit conversion, I would memorize this one. I find it the most useful. That's the one that I use. And I'll just convert to inches, convert to centimeters, then convert to whatever unit I need. But so the steps for converting, you choose a conversion factors. These generally can be looked up on tests and quizzes. They will be given. Arrange the conversion factor into the appropriate form so unwanted units will cancel out. So if you're going from inches to centimeters, you choose 2.54 centimeters over 1 inch. If you're going from centimeters to inch, you choose 1 inch over 2.54 centimeters. And then you either multiply or divide to calculate the answer. And anticipate if your answer is going to be a bigger number or a smaller number than the one you started with. If you're going from a smaller unit to a bit larger unit, the number you're going to get will be smaller, and vice versa. If you're going from a larger unit to a smaller unit, the number you're going to get will be bigger. So here is an example going from kilometers per hour to miles per hour. 1 kilometer is 6.21 miles, which means 1 kilometer per hour is 6.21 miles per hour. We're actually only converting the kilometers here. The hours are staying the same. So 50 kilometers per hour is our starting value. We can multiply by 6.21 miles per kilometer and get 31.05 miles per hour. The kilometers will cancel and we'll just be left with miles. And either conversion factor could be used. You could also use the fact that 1 mile is 1.61 kilometers. And so going from 50 miles per hour, you can either do 1 kilometer over 0.621 miles per hour and get 80.5 kilometers per hour, or 50 miles per hour times 1.61 kilometers per hour over 1 mile per hour. And it's possible to go from this value to this value just by dividing 1 by, 1 over 0.61 gives you 1.61. Generally, on a test or a quiz, I'm only going to do one of those ratios. So you can use that one. But both of these will give you the same. Going from 50 miles per hour, you get 80.5 kilometers per hour. And you can also do multi-step conversions. So if you wanted to go from inches to meters, for example, starting value was 22 inches. You can then convert to centimeters by multiplying by 2.54 centimeters per inch, and then go from centimeters to meters by multiplying by 1 meter per 100 centimeters to get a final conversion value of 0.56 meters. So 22 inches times 2.54 centimeters per inch times 1 meter per 100 centimeters gives 0.56 meters. So here, 10 yards. 1 yard is 0.914 meters. So we want to figure out how many meters first to 10 would be if you were measuring in meters. So if we start with 10 yards, we multiply by 0.914 meters per yard, and we get 9.14 meters. Here we have a road in Peru. It has an altitude of 4,843 meters, and we'd like to know what it is in feet. Well, 1 meter is 3.28 feet. This is a conversion factor you can look up in your book. There's a table of conversion factors. So 4,843 meters times 3.28 feet per meter is 15,885 feet above sea level, which is 1,775 feet higher than the top of Pikes Peak. Very tall mountain. The Andes are tall. So here's another example of interconverting in the metric system. You have 1.6 times 10 to the minus 7 millimeters. You want to write it in as micrometers. 1.6 times 10 to the minus 7 millimeters times 1 meter over 10 to the third millimeters, or 10 to the minus 3 meters per millimeter. You could use either one of those. Millimeters cancel, and then 1 micrometer over 10 to the minus 6 meters, and that will give you micrometers. Meters will cancel. So that's 1.6 times 10 to the minus 4 micrometers as a result. Here we have 1.6 times 10 to the minus 7 millimeters as picometers. So same conversion for millimeters to meters, but now we're doing picometers. So 1 picometer is 10 to the minus 12 meters. So 1.6 times 10 to the minus 7 millimeters times 1 meter over 1,000 millimeters. Millimeters cancel, times 1 picometer over 1 times 10 to the minus 12 meters. And this will give you 1.6 times 10 to the 2 picometers, or 160 picometers. So if you did want to write 1.6 times 10 to the minus 7 millimeters in a nice unit, you'd probably use picometers. So here are a couple of problems. Let's convert 1.235 meters to nanometers. So let's go through this process. 1.235 meters times 1 nanometer. 1 nanometer is 10 to the minus 9 meters. So we divide by 10 to the minus 9, which is the same as multiplying by 10 to the 9. So this is 1.235 times 10 to the 9 nanometers, or 1,253,000,000 nanometers. Nanometers are small. And here we have 1,235 centimeters. We want to convert that to meters. Well, 1 centimeter is 10 to the minus 2 meters. So 1,235 centimeters times 10 to the minus 2 meters over 1 centimeter is 12.35 meters. And here is a little bit more complicated problem. We want to convert 6 feet 5 inches to centimeters. Well, the first thing we want to do is we want to get rid of this mixed unit. We have 6 feet 5 inches. We'd like it to all be in one unit. The easy one to do is inches. So the first thing we're going to do is we're going to figure out how many inches 6 feet is. 1 foot is 12 inches. 6 feet is 72 inches. Then we'll add an extra 5 inches and get a total of 77 inches. Now we're going to convert 77 inches to centimeters. 77 inches times 2.54 centimeters per inch gives you 195.58 centimeters. However, you should probably round this off to the nearest centimeter because these are sort of excessive precision. So I would probably say this is 196 centimeters, but that's the exact number you get on your calculator. Significant figure-wise, I guess you would maybe do, yeah, I do 196. I probably should have written it as 6 feet and 5.0 inches, and that would have resolved it, but yeah. Here, let's convert 124 nanometers to centimeters. Well, nanometer is 10 to the minus 9 meters. A centimeter is 10 to the minus 2 meters. So we have to do 2 conversions. First, nanometers to meters. So 124 nanometers times 10 to the minus 9 meters. We could sort of replace that n with 10 to the minus 9 is another way to think about it.
And then to go to centimeters, 1 centimeter divided by 10 to the minus 2 meters. So 124 times 10 to the minus 9 divided by 10 to the minus 2 is 124 times 10 to the minus 7. And if we put this in scientific notation, we have to move the decimal place 1, 2 places to the left, increasing the power by 2. We get 1.24 times 10 to the minus 5 centimeters, or 0.000124 centimeters. Here, if we convert 3.45 kilometers to millimeters, 3.45 kilometers, each kilometer is 1,000 meters. So we do 10 to the third meters per kilometer, and each millimeter is 10 to the minus third meter. So 1 millimeter is 10 to the minus third millimeter. So 3.45 kilometers times 10 to the third divided by 10 to the minus third gives us 3.45 times 10 to the 6 millimeters, or 3,450,000 millimeters. Now I want to quickly introduce significant figures before I let you go, but we'll go over this in more detail next week. I just want to introduce it to you because you can also pick up the significant figures worksheet up here that's due week after next. But I just want to go over the idea of significant figures. So significant figures is a way we can express how precisely we measured something. And we want, when we do calculations with numbers, we want to preserve that information about how accurate or how precise our measurement was. Well, how precise our measurement was. They don't tell us anything about how accurate it is. We could be very wrong, but still be very precise. So any mathematical operation, such as multiplication, division, addition, or subtraction, shouldn't give you more significant figures than you started with. That's the general idea. There is a technicality to deal with addition and subtraction. Usually, but I'm not going to be picky about it in this class. Strictly speaking, addition and subtraction can give you more decimal places than you started with, while multiplication and addition is significant figures. But usually that doesn't make a difference. And I will not mark you wrong if you just use significant figures. Both will be, I will consider both correct in this one. So for example, 6.8 has 2 significant figures and 1.67 has 3 significant figures. The way you count significant figures, all non-zero digits are significant. All zeros in between non-zero digits are significant. And leading zeros are never significant. Trailing zeros are significant if you have a decimal. The general. So 6.8 times 1.67. If you plug that into a calculator, you'll get exactly 11.356. Because your calculator just gives you the best answer it can give. But if I were to express that I only had 2 significant figures of precision in one of my measurements, I'll have to round this down to 2 significant figures. So the correct answer for this 6.8 times 1.67, taking into account significant figures, would be 11. Because this implies that I measured, that I know that value more precisely than I actually do. This is particularly important when you divide, because division tends to give you lots of extra decimal places. So 6.8 divided by 1.67 on your calculator will give you 4.07185564, and possibly even more. This just particular calculator ran out of digits. But to express this correctly, you would round it to 4.1. Not all of these are significant, only the first 2 are. Because we use the least significant figures of our input for our output. So that's sort of the general rule of thumb. Look at your inputs. Whichever one has the least number of significant figures is what you'll have to round your output to. And it's best to wait until the end to round, because you can have errors built up from rounding. So the general rule is report only as many significant figures in the result as there are in the quantity with the least significant figures. So 6.8 centimeters divided by 1.67 centimeters, you would round to 4.1. The limiting term is 6.8 with two significant figures. Here, 5.678 plus 11.11, you would round to 16.80. You round up from 16.797. The limiting term here is 11.11 with four significant figures. Strictly speaking, for addition, you use the number of decimal places. The limiting term is 11.11 with two decimal places. You can see how significant figures and decimal places give you the same answer. So the rules for significant figures. The worksheet is about counting the number of significant figures in various numbers. All non-zero digits are significant. So 23.4 and 234 both have three significant figures. Zeros are significant if they're between two non-zero digits. Zeros in the middle always count. So 20.5 has four significant figures. 20.05 has four significant figures. 407 has three significant figures. Your block of significant figures will always be one continuous block. There aren't going to be any gaps. Leading zeros on the front, never count. So 0.0000035 has two significant. These are just telling you the magnitude. The 35 is the important part for precision. And trailing zeros to the right of non-zero digits, you need to determine from context. 45.0 has three significant figures, but 4500 probably only has two. The general rule of thumb is trailing zeros count if there is a decimal point, they don't if there isn't. And I will follow that rule on all testing quizzes. Sometimes when I want trailing zeros to count, but I want to use a nice round number, I may write something like 100 and then just put a decimal point at the end because I want it to have three significant figures. I'll do that on tests and quizzes a lot, just to use nice round numbers to make the math a little easier on the test or the quiz, but to have the right number of significant figures. So if there is a decimal point, even if it's just sitting at the end, that tells you that these are all significant. One of the nice things about this, if a number is in scientific notation, all those numbers in the mantissa, in the number part, are always significant. Now, there are a couple of exceptions. If you have an exact number, or like a number in a formula, like number of people's items, etc., or where it's an exact count, or the values in formulas, like if they're like a 2 or a half in a formula, those are assumed to have unlimited significant figures. Basically, you don't need to worry about them. And in the process of determining the allowed number of significant figures, you also have to round the numbers off. The rule for that is you look at the first digit you're going to drop. If that digit is from 0 to 4, you just drop it, you round down. And if it's from 5 or above, you round up. That is all I'm going to cover for today. I'll see you guys next week. Have a nice weekend and holiday on Monday. Yes, and everyone please grab the significant figure worksheet up here. This is due. Though it is also available on Blackboard, so you can just download it, or I'll have copies. We want to grab one later. I'm going to stop sharing and